Hello. I wanted to help you out with number 7, just because in period 4, there was a whiteboard where I missed being able to help them, and I want to show you that. So this was their whiteboard. I took a picture of it, and if you look, the force diagram they did is beautiful. They have weight going down, friction, force due to the rope, and normal force. So that was perfect. Let's see, weight, tension due to rope, which this group called capital F for force due to rope. Normal, friction. The problem happened is right here. Okay, this is a constant velocity situation, but regardless, if you'll notice, the error they made was when they summed the forces. They have this force going this way and that force going that way, when in fact you're adding the vectors head to tail. You'll need to add all of them head to tail. So what it should have looked like was, let's see, there's an easy way I can do this. I saw a group today do it. Let's see, you got weight, friction, normal, perpendicular to friction, right? And then tension due to rope. So it should look something like that. And you have a right triangle right there. Let me try to do that a little better. You have a right triangle here, okay? Now let's label our forces. This is normal. This is my friction. This one here is my tension. And this one here is my weight. And if you'll notice, all the arrows are placed head to tail, meaning that all I'm doing is adding the forces as vectors. So I've been calling this a vector addition diagram. This would be a very important step. And this is essentially what we learned last semester. In order to use Newton's laws, you'll need this kind of a diagram. And it comes right out of your force diagram. And it helps you adjust, it helps you figure out the lengths of the arrows, which essentially tells you the magnitude of each of your forces. The rest, the problem, this group was getting a negative value for their force, but doing it this way, it shouldn't be a problem. You should get a positive value. You know the weight is 14,000 newtons, right? Because the mass is 1,400 kilograms. From the weight, you can figure out that this one, let's see, let's figure out an angle here. If your ramp is tilted by, 20 degrees in this case? If your ramp is tilted 20 degrees, let's see here, this angle right here, your normal force will be tilted 20 degrees also. So that angle there is going to also be 20 degrees. So I'll put a little arrow there and write 20 degrees. And that means that just worrying about the lengths of these, the length of tension minus the magnitude of my friction should be equal to W sine 20 degrees, right? Maybe you'd be more comfortable if I started with sine 20 degrees. So why don't I slow it down a little bit here? Okay, so sine 20 is going to be T minus F over, that's tension minus friction. I'm calling this force here tension, over weight, right? So when I multiply both sides by weight, I get this, and therefore tension is going to be W sine 20 plus friction force. And working from there, I would need to find my normal force in order to find my friction. So I should probably do that now. That's going to come from cosine 20 degrees. So cosine 20 will be normal force, that's this length here, over my weight. So normal force is going to be my weight times cosine 20 degrees. Okay, so then friction is going to be, I think the coefficient is given as, let's see here, let's scroll to the top, see what the coefficient of friction is. This is a kinetic friction, it's 0.4, okay. So I'm going to multiply 0.4 times my 14,000 newtons times cosine 20 degrees, okay? And that's going to give me my friction force. And then over here, I'm going to have to take my 14,000 newtons times my sine 20 degrees plus whatever I get from my friction, okay? So I'll have to plug what I get here in right here. And that should help you with number 7. What is the force of friction between the block and the incline? Well, that's right here. What is the force applied to the block by the motor? Okay, that's right here. Okay, and then when you want to find the power output of the motor, there's actually a few ways you could do it. It's a good idea to draw an energy flow diagram for every problem. It just helps you understand the problem better. So I'll put block and it's connected to a rope. And then let's say this is a motor right here. And then later on, that's the motor. It's moving with constant velocity. So the motor is doing work on the block, and at the same time, there's energy dissipating. That's why the EG, EK, elastic, none of that is changing. So you have no energy, there's no change. So your equation is going to be work minus E dis equals 0. So in other words, whatever work is done on the block is dissipating out of the block system. So in order to figure out this work, we would just need a graph of F versus delta X. Should look like this. So power is going to be work over the change in time. Now in this case we don't have a time interval. So what we can do is say power is equal to F change in position over change in time. And we can say that this as a whole is our velocity. So power, and since our velocity in this case is average velocity over time or instantaneous velocity, actually power average power and instantaneous power are going to give you the same number. Whatever force you get for the tension in the rope, that is right here, whatever value you get here, you just take that value and you multiply that by your speed. And your speed's not changing, so your average speed in this case is the same as your instantaneous speed, which means your average power and your instantaneous power are the same number. So you take whatever value you get for the force on the block due to the rope that's attached to the motor. And I think in this case, your speed is 1.5 meters per second. So you would multiply by your 1.5 meter per second. And that should do it. That should give you your value for power. Anyway, I hope you enjoyed it. That's number 7. I hope that helps. Sorry for the group that I should have caught that mistake, or somebody in the class should have caught that mistake while the whiteboard was up. I'm sorry we didn't help you then and there. Hope you have a good day. Thanks for watching.